Okay, welcome to section 2.2c, and I think this is going to be a lesson that you guys really enjoy for a couple of reasons. First of all, let's be honest with ourselves here. Every lesson in my class is amazing, so that's just a given. But specifically with regards to this one, there's nothing new conceptually that I need to teach you in this section. We're still practicing the same exact normal word problems we were in the last lesson, 2.2b. So you don't have to wrap your head around any sort of new concepts right now. We actually get to practice the stuff we already learned, which will be really good and make you feel more comfortable with it. Also, I'm teaching you guys an easier way to do the problems that we already learned. Using the table is a little bit tedious and has some extra steps to it, where I'm going to show you in this lesson how to do those same exact problems on the calculator, which is going to be end up being something you guys will really like. So this should be a good lesson without too much of a struggle. So let's get to it. There are going to be a couple commands we use on our calculator to do normal problems. And I'm going to have you write down what the commands are first, and then I'll show you where to find them in just a sec. So the first command we're going to get very comfortable with this year is called normalcdf. And I'll show you where to find that in a minute. CDF stands for cumulative density function. Cumulative meaning we do less than or equal to's, greater than or equal to's, and stuff like that. There's another command in the same menu called normalpdf. PDF stands for probability density function. It's when you do an equals problem, which we don't do. We don't find the probability we equal a certain value. You would use this command on your calculator if you were going to graph a normal distribution. It's possible to do that. For AP stats, we will never use the PDF version, always the CDF. So the other command that we need to know is for finding boundaries, which is called inverse normal. invNorm is the name of the command. And let me show you where to find those. So this is actually going to be a new menu on your calculator you probably weren't aware of, but we will use it a super ton this year in AP Stats. So this is the first of many times you will see that menu. What you're going to need to do is go second, and it's called the distribution menu, which is written right here on the vars variables key in blue. So second, distributions. And right now, this looks just crazy to you guys, but we will learn a bunch of the commands in this menu over the course of our time together. PDF, again, we do not use. That's if you were going to graph a normal curve on your calculator. We want number 2 and number 3, CDF, and an inverse normal. Those are our two for right now that we care about. And when you click on them, I'll show you how to use them on a problem in a minute. It's going to ask you for a few things. But note that the mean and the standard deviation, if you don't specify them, default to 0 and 1, which is that standard normal distribution that we've already talked about. So if you don't enter a mean and a standard deviation in the calculator, they do default to our standard normal, which is mean 0, standard deviation 1. So let's jump into a word problem here, and you guys will see that this lesson really isn't bad at all. Oh, before we do that, reminder of the 3 things I expect you guys to do when you're solving a normal problem. 1 is give me a detailed picture, draw a curve, shade it, show the work, write the variables, etc. After you do your picture, you're going to actually show your work, and then you're going to answer the question in context. So doing these 3 things makes these problems pretty straightforward. So our big context for the day is looking at a cereal manufacturer here. And cereals always have, and most products you can buy at the store, have a weight on them. But obviously, if you think about it logically, not every single box of cereal weighs exactly what they say it's going to. So if a box is labeled as 16 ounces, they have to decide, like when they're setting up their machine for like how much cereal do I put in, what the average should be. So on average, they try to make it so the distribution of the amount of cereal is normal. So some boxes get a little less than they're supposed to, some get a little more than they're supposed to, but they average out to whatever. Now, if you put it exactly at 16 for the average, just think about what that means if it follows a normal distribution. It means that literally half of your cereal boxes weigh less than they're supposed to. They weigh less than 16 ounces, which is a good way to make customers angry. So what they actually do, and this is something that I assume happens in real life here, they set the mean to be a little bit higher than it's advertised as. Because if you get a little too much cereal, you're not going to be mad about that. And that way, when it follows its normal distribution, most of the boxes will have an acceptable weight to them. So they ask us for this first problem about what proportion of cereal boxes will be underweight. Anytime you know something is normally distributed, your first move is always going to be to draw a nice curve here and to label up the problem. The mean for this problem is stated to be 16.3 ounces. So they're setting the mean a little higher than what they advertise it to be. And the standard deviation for this problem, that was a bad line, is supposed to be 0.2 ounces. And some sort of context down here is going to be good. So this is going to be like weight of box, weight of cereal box in ounces. So get a little context right there. They ask us in the problem, what percent of boxes will be underweight? Underweight, if you recall, will be 16 ounces or less. So 16 will be somewhere in that area. And then we're looking for what percent of boxes will fall into that region, okay? Now, if this was last lesson, we would go find a z-score, we would take that z-score, we would use the table, and it would be a lot of work to do all that. Or we can turn to our calculator and do a good old normal CDF. So on our calculator, if we're looking for an area, we're going to use the normal CDF command. When you choose that, it's going to ask you, where am I finding the area? Tell me where to sandwich the area that I want. So what I want is I want this red area right here. The lower end to this red area is technically, it's going to keep on going to that side just forever. But the thing about it is, like with the standard deviation this low, you're not going to have to go too crazy because eventually, like no cereal boxes weigh less than 0 ounces, for example. The calculator defaults to -1 E99, which is scientific notation. That's -1 times 10 to the 99th power, which is just crazy big negative number. I can leave that alone, and that will be totally fine. It's just really big negative number. I can also make it a 0, and that's cool too. Or I can even do something like -999. Like, it's really kind of flexible what you end up doing for your lower bound here. You'll get pretty much the same answer. The upper bound, on the other hand, has to be where the area stops, which is at the number 16. So my lower bound I'm going to leave as 0. My upper bound I'm going to make a 16. The mean for the problem is a 16.3. And the standard deviation for the problem is a 0.2. So you're going to type all of that in the calculator, and then you're going to hit paste. And it will tell you, if you hit enter again, the answer. So when you actually write down your answer for this problem, your work for this problem, you're allowed to write down in calculator speak what you did. So I'm going to put down normal CDF. But the AP test is very clear that they will take off if you just write like 0, 16. You have to label what each of these commands that you typed in was. So the first thing we did is we typed in our lower of 0. Then we typed in our upper bound of 16. Then we typed in our mean of 16.3. And then we typed in our standard deviation of 0.2. So when you do this, if you're doing it the calculator way, you have to make sure you label what each of these things means. When we did that, the calculator gave us our answer. I lost my calculator. Let me see if I can bring it back. So if we look at it again, normal CDF, we typed that all in and we got 0.0668. 4 decimal spots is pretty typical here. So 0.0668. And then just restate the answer in context to get full credit. So what I would need to do here is I would need to say approximately 6.68% of boxes will be underweight. And that's how you answer one of these questions. Same basic process, just now you use normal CDF instead of finding a z-score and looking it up in the table. You don't have to find a z-score to use this method, which is really nice. So go ahead and try out that second problem for yourself and pause me here, and I'll just put an answer on this one rather than walking you through it again. This time, it's going to be more than 16.4. So when you draw your picture, think about what your lower and your upper bounds are going to be. Okay, so I have a solution written out for this problem right here. And I want to point out just a couple quick things. Since it was more than 16.4 that they asked us for in this problem, I can make my lower bound the 16.4. That's the left side of my part. My upper bound is going to be a big number. I just picked 9999. Like you could do 100, 1,000. Like as long as it's like not something really silly like 17, where it could actually be in the picture. Just pick something far off the picture, 1,000, 10,000, a million, and you're good. We're going to get just about the same answer because no values are that far away. And if you do that, you're going to get 0.3085. When you do one of these problems with the table method always does a left tail area. Whoops. So the table always does problems from the left side, like this. But if we use the calculator, we can just specify what we want and get our answer right away. So there is no need for a 1 minus on problems like this when you use the calculator. You just do normal CDF, you specify your lower and upper, and you get the answer. The next problem on the next slide here, I'm not even going to do. You would just do a normal CDF with a lower of 16.2 and an upper of 16.4. That's pretty straightforward for this one. Nice and easy. Less work than the table for sure. You should get 0.3829 if you actually do this one. Let's move on and talk about the other kind of problem. Now they're asking us for the 20th percentile. So my mean is still a 16.3. My standard deviation is still a 0.2, but now I don't know my value on the graph. What I do know is that it's at the 20th percentile. So the area for this piece over here is a 0.20, and I'm looking for my value right there. So when you want the area, you do normal CDF, like the first couple. When you don't, or when you know the area and you want the boundary, you have to use the other command in our menu, which is inverse normal, number 3. When you do inverse normal, I need to make sure I specify on this part. Depending on what kind of calculator you have. My calculator only says area. And if you have an older calculator, yours will be the same. If it just says area, it only does the left area, like our tables when we were doing those earlier. So if it just says area, you have to assume it means left area. If you have a newer calculator, you might have an option here where you can choose from a left area, a center area, or a right area. And you can just specify which one you want, which is handy. So if you have that, feel free to use it. If you don't, like me, we have to assume it means left area. Now on this problem, the thing I want actually is a left area. It's this blue part right here. So I'm going to put area 0.20. We're going to learn what to do when it's not the case on the next problem. So if you have a left, center, right, you would choose the left area for that. My mean was 16.3, and my standard deviation was 0.2. And you just type it in the calculator like before. Now it gives me an actual number here for my boundary. So it's 16.13-ish. So I did an inverse normal. And again, I need to label my commands. The left area is 0.20. The mean is 16.3. The standard deviation is 0.2, and I forgot what I said. My answer was 16.13. And then you could, of course, write down the full context. 16.3 ounces represents the 20th percentile for cereal box weights, blah, blah, blah. Okay, so not that much worse than our original. What weight represents the cutoff for the heaviest 5% of cereal boxes? So on this problem right here, the heaviest 5% is going to be this part way over here on the ends. And I still have the same mean. I still have the same standard deviation. When you do like 8 of these in a row, it gets a little tedious. But on a quiz, there's going to be 1 or 2 of them tops. So you should draw the full picture and label it. And don't be lazy with it. You might lose credit. So again, I know the area. That's when I do an inverse normal. But if you have one of my calculators, it's only a left area. So I need to do a 1 minus 0.05, and my area is going to be 0.95. Okay? If you have the option to choose right area 0.05, great. You can do that and it's fine. Just specify what you did. I got 16.63 on this one. So when I actually type that in, inverse normal, and when I write out my work for this one, specify the area you did. So I did a left area of 0.95, or you might have done a right area of 0.05. Either way is cool. I forgot what my answer was again. So I got that. I have my mean of 16.3, got my standard deviation 0.2. It's like 16.6. 16.63 is my answer. And then again, you give nice little context and you finish it up. We have one more trickier question to end this video. And it's one of those questions like in the last video where they give you like part of the information, like what's the standard deviation or what's the mean or what's the value that goes with it. So I'm going to go ahead and I want to sketch a picture here to help me organize my thoughts. Pictures are just great for making sure you understand what's going on. Now they want the mean to be 16.1. So they don't want to pay for that extra 0.3 ounces. They're trying to lower it to a 16.1. If you do that, though, you're going to have more boxes that are underweight. But if they can manipulate their standard deviation and make that smaller, then they're not going to spread out as much. So maybe they can lower the mean and save money on cereal, and then lower the standard deviation so the boxes are more consistent and save money that way. So they want to know what standard deviation their distribution must have so that at most 10% of the boxes are underweight. So if we look at this problem here, the underweight is 16 ounces, and we know that the area right here is going to be 10%. Okay, so this is organizing our thoughts for the problem right here. Since I know the area, I'm going to try to use inverse normal for this problem. When I go to use inverse normal, the issue is that it asks you for the mean and the standard deviation as a package deal. Mean is 16.1 now, that's easy, but I don't know the standard deviation that goes with it. That's like the whole purpose of the problem. So what you need to do in this sense, if you don't have the duo, you need to use standard normal instead. So my area for this problem is going to be a 0.10. My mean, I'm just going to default to standard normal here because I don't know the full pair. And when I do that, this number that it gives me is a z-score because I did a standard normal. So I'm going to have z equals negative 1.28. That's not the answer to the question. So after I get my z-score, I just do like the last video, a little bit of easy algebra here. Z-score equals my value minus my mean divided by my standard deviation. And then you just use algebra to get your variable of interest by itself. So on this problem here, what I would do, 16 minus 16.1, and then I would have to divide by negative 1.28. So anyway, you do algebra, and then you get a standard deviation. My old standard deviation was like a 0.2. This one is much smaller, 0.078. So you have to lower your standard deviation quite a bit to make the problem not have too many boxes that are underweight. So the calculator, not any worse in terms of what you have to do to think about the problem, but easier to actually find the solutions, which is a great thing.